In our previous modules, we have discussed large sample distribution of moments, large sample distribution of different summary measures based on moments, and also obtained the large sample distribution of correlation coefficient. In this module, we shall discuss large sample distribution of sample quantiles, both marginal and joint. Also obtain the large sample distribution of some quantile based measures like sample range, sample mid-range and sample quartile deviation. And finally, we shall obtain the large sample distribution of median and discuss some examples with different issues with asymptotic distribution of extreme order statistics. As indicated earlier, we have discussed large sample distributions of summary measures based on moment statistics. In this module, we shall discuss asymptotic distribution of sample quantiles and then obtain the measures based on sample quantiles. So, let us start from the definition of sample quantile and population quantile. Let xi I equal to 1 to n be IID observations from a continuous CDF fx, and due to continuity all the observations are distinct with probability 1. Suppose x ordered 1, x ordered 2 up to x ordered n denote the full set of order statistics, and in particular x ordered r is the rth order statistic. For p belonging to open interval 0 to 1, for p belonging to open interval 0 to 1, the pth order population quantile is defined as xi p, which is f inverse p, and the corresponding sample quantile is defined as x ordered k, where k is nothing but the greatest integer contained in np plus 1, where n is the sample size. We shall obtain the joint asymptotic distribution of x ordered r and x ordered s. Note that order statistics are not explicit functions, and hence delta theorem is not straightway applicable here. So, we need to develop some alternative methods in such a case. If x has a distribution f where f is continuous, then it is well known that the distributions of f inverse u and x are identical, where u has a rectangular 0 1 distribution. Thus, for a full set of n observations, we find u ordered j, that is jth order statistic for u observations as f x ordered j, where uj is as defined earlier. Thus, we first find the asymptotic joint distribution of order statistics from a rectangular 0 1 population, and then use delta methods to obtain the joint asymptotic distribution of general order statistics in a convenient way. So, we start with few lemmas. The first lemma is like this: if yi are IID exponential random variables with mean 1 for I from 1 to n plus 1, then the joint distribution of y1 divided by summation I from 1 to n plus 1 yi, y1 plus y2 divided by summation I from 1 to n plus 1 yi, up to y1 plus y2 plus up to yn divided by summation I from 1 to n plus 1 yi is the same as the joint distribution of u ordered 1, u ordered 2, u ordered n, that is the full set of order statistics from a rectangular 0 1 population. So, how to prove this result? This result is not very immediate or very well known, but is very useful. So, let us first find the distribution. First of all, note that the joint distribution of yi is simply e to the power minus summation I from 1 to n plus 1 yi for 0 less than yi less than infinity for every I, and we transform zj, that is we define new variables zj as y1 plus y2 up to yj for j from 1 to n plus 1, so that we get the Jacobian matrix J from z to y as a matrix with elements in the first row as 1 and minus 1 and then all 0. In the second row we have the first element 0, then elements 1 and minus 1, and then the remaining are 0, and in this way we get the last row elements as all 0 except for the last two, which are 1 and minus 1 respectively. Now one can observe that the first row contains two non-zero elements, and the first column contains only a non-zero element. So if we expand this matrix, expand the determinant of this matrix using the cofactors of the first column, we find that in a recursive way that the determinant of this Jacobian is 1, and since yi are all positive, we have the relation 0 less than z1 less than z2 less than up to zn plus 1, and hence we get the joint distribution of z1 z2 zn plus 1 as e to the power minus zn plus 1, where the range of the variables are given as 0 less than z1 less than z2 less than zn plus 1 less than infinity. Next we apply another transformation which is Vj equal to Zj by Zn plus 1 for j from 1 to n, and Vn plus 1 equal to Zn plus 1. So we get Zj equal to Vj multiplied by Vn plus 1 for j from 1 to n, and Zn plus 1 equal to Vn plus 1. Thus we naturally get the Jacobian matrix which is given in the text, and expanding through the cofactors of the last column, the determinant of the Jacobian matrix can be found as Vn plus 1 to the power n. Hence the joint distribution of Vj for j from 1 to n plus 1 is of the form n factorial multiplied by the indicator of 0 less than V1 less than V2 less than Vn less than 1 multiplied by e to the power minus Vn plus 1 multiplied by Vn plus 1 to the power n divided by gamma n plus 1 multiplied by indicator Vn plus 1 greater than 0. Hence the joint distributions of V1, V2, Vn and Vn plus 1 split in two separate components. So from the first principle of independence, V1, V2, Vn, that is the joint distribution, the variables V1, V2, Vn is independent of Vn plus 1, where the joint distribution of V1, V2, Vn is simply that of n order statistics from rectangular 0, 1 population. However, from the PDF, the representation as given in the previous page PDF, it is natural that Vn plus 1 has a gamma distribution with rate unity and shape n plus 1, and this completes the proof. So what you observe from this result? From the above result, it is evident that summation I from 1 to r yi divided by summation I from 1 to n plus 1 yi and summation I from 1 to s yi divided by summation I from 1 to n plus 1 yi has the same distribution as the joint distribution of u ordered s for r less than s, where as earlier u ordered r is the rth order statistic from a sample of size n from rectangular 0, 1 population. Thus we have expressed the equivalence of joint distribution of order statistics with a function of sums of IID random variables. This equivalence enables us to apply CLT, that is central limit theorem, on the equivalent sets of random variables. Actually we cannot use central limit theorem, what we have discussed earlier, on order statistics, but we can apply CLT or some other type of convergence results for sums of independent IID random variables which are yi. So that is why this representation is necessary. Next, consider our second lemma. If square root of n multiplied by r by n minus p1 tends to 0 and square root of n multiplied by s by n minus p2 tends to 0 for some 0 less than p1 less than p2 less than 1, then the large sample distribution of tr by n plus 1, ts minus tr by n plus 1 and tn plus 1 minus ts by n plus 1 is 3 variate normal with means p1, p2 minus p1 and 1 minus p2, and dispersion matrix as a diagonal matrix with elements p1, p2 minus p1 and 1 minus p2, where tk is the partial sum summation I from 1 to k yi. First of all, for a proof, consider the representation square root of n tr by n plus 1 minus p1 equal to square root of n tr by n plus 1 minus r by n plus 1 plus square root of n r by n plus 1 minus p1. By central limit theorem, the first term in the right hand side of above converges in distribution to normal 0 p1, that is to a normal variable with mean 0 and variance p1, whereas the second quantity converges ordinarily to 0 due to the assumption that square root of n r by n minus p1 tends to 0 as n tends to infinity. Therefore, by Slutsky theorem, square root of n tr by n plus 1 minus p1 converges to a normal distribution with mean 0 and variance p1. In a similar way, the other convergences can also be proved using central limit theorem for IID random variables in combination with the facts that square root of n multiplied by r by n minus p1 tends to 0 and square root of n multiplied by s by n minus p2 tends to 0 as n tends to infinity. However, the variables are independent exactly because they are based on disjoint sets of IID random variables, and therefore they are of course independent asymptotically, and we have the result. Next, consider our third lemma. If square root of n multiplied by r by n minus p1 tends to 0 and square root of n s by n minus p2 tends to 0 with 0 less than p1 less than p2 less than 1, then the joint distribution of the joint asymptotic distribution of u ordered r and u ordered s is bivariate normal with mean vector 0 and dispersion matrix with elements p1 into 1 minus p1 and p1 into 1 minus p2 in the first row, and in the second row the elements are p1 into 1 minus p2 and p2 into 1 minus p2. So, for a proof, first of all we note that from lemma 1 the equivalence, that is the joint distribution of ur and us is the same as tr divided by tn plus 1 and ts divided by tn plus 1, and we can write tr by tn plus 1 as tr divided by tr plus ts minus tr plus tn plus 1 minus ts, and similarly we can express ts as tr plus ts minus tr and tn plus 1 as defined earlier. So, why to use such a representation in terms of trs? Because we have obtained the large sample distributions of tr, ts, ts minus tr and tn plus 1 minus ts in lemma 2. So, representing u ordered r and u ordered s in this term in terms of these variables, we can find the large sample distributions using lemma 2. So, we at once define the vector valued function with 3 arguments u1, u2, u3 as u1 divided by u1 plus u2 plus u3, and the other component is u1 plus u2 divided by u1 plus u2 plus u3. Then it is easy to observe that g of tr divided by n, ts minus tr divided by n, that is if we substitute u1 as tr by n, u2 as ts minus tr by n and u3 as tn plus 1 minus ts by n, we find the two component vector with elements tr by tn plus 1 and ts by tn plus 1, and naturally it has the same distribution as u ordered r and u ordered s. Hence, with already introduced notations, we get the G matrix as a 2 cross 3 matrix with elements 1 minus p1, minus p1 and minus p1 for the first row, and the elements 1 minus p2, 1 minus p2 and minus p2 in the second row. Thus, applying delta theorem, we have the large sample distribution of u ordered r and u ordered s as a bivariate normal with mean 0 and dispersion matrix G multiplied by the diagonal matrix with elements p1, p2 minus p1 and 1 minus p2, whole thing multiplied by the transpose of G. Now, a simple matrix multiplication gives this asymptotic dispersion matrix as a matrix which has the desired form as given in the result, and therefore we get the result. So, for order statistics, the result has three components. First, we have expressed the joint distribution of UR and US in terms of some sums of IID random variables, and then using CLT and analogy with the order statistics, we have obtained the large sample distribution of U ordered R and U ordered S. Now we can at once generalize lemma 3 because we can have more than 2 order statistics. If square root of n multiplied by Ri by n minus Pi tends to 0 for I from 1 to k, for 0 less than P1 less than P2 less than up to Pk less than 1, then the joint asymptotic distribution of U ordered R1, U ordered R2 and U ordered Rk is k-variate normal with mean 0, and dispersion matrix P multiplied by the transpose of 1 minus P, where P is a vector with elements P1, P2, Pk, and 1 is a vector with all elements unity, and therefore 1 minus P is a vector with elements 1 minus P1, 1 minus P2, 1 minus Pk. So let us come to our final result, that is the order, that is the asymptotic distribution of order statistics. If x ordered I are order statistics from a continuous distribution function f having continuous density small fx such that small fx is positive in a neighborhood of population quantiles xi pi, then the joint distribution of x ordered R1, x ordered R2 and x ordered Rk is a k-variate normal with mean vector 0 and dispersion matrix sigma, where the elements of sigma are sigma ij, where sigma ij equals pi multiplied by 1 minus pj whole thing divided by fpi into f xi pj. So how to prove this result? The proof of the above result follows from a simple application of delta method. Since by the assumption of the result f is continuous and hence f inverse is well defined, we define the vector valued function g with arguments u1, u2, uk as f inverse u1 is a with arguments u1, u2, uk, and this g has k, and hence f inverse is well defined. So we define the vector valued function g with arguments u1, u2, uk, and this vector valued function has k components which are f inverse u1, f inverse u2 up to f inverse uk. Then with the already introduced notations, G, the matrix with elements as differentials, is a diagonal matrix with elements partial derivative of f inverse ui, that is f of f inverse ui to the power whole to the power minus 1, that is 1 by small f of capital F inverse ui. Therefore, we get the asymptotic joint distribution of x ordered R1, x ordered R2 and x ordered Rk as k-variate normal with the desired form of dispersion matrix, and we get our result. So next we pass on to our next topic, which is asymptotic marginal distribution. Once we find the asymptotic joint distribution, the asymptotic marginal distribution is a routine. So with the already introduced notations and assumptions, if R equal to box NP plus 1, then the large sample distribution of x ordered R is normal with mean xi p and variance sigma square, where sigma square is p into 1 minus p divided by f square xi p. So next we find the asymptotic distribution of sample quartile deviation and median. For a sample of size n, sample quartile deviation is defined as q hat, which is the difference of x ordered s and x ordered r divided by 2, where r is box n by 4 plus 1 and s is box 3n by 4 plus 1. If q denotes the population quartile deviation, then it follows from the joint asymptotic distribution of sample order statistics that square root of n, that is large sample distribution of q hat, is normal with mean q and variance tau square, where tau square can be evaluated as 1 by 64 whole thing multiplied by 3 by f square xi 1 plus 3 by f square xi 3 minus 2 by f xi 1 f xi 3. However, for a symmetric distribution f xi 1 equal to f xi 3, and hence tau square reduces to 1 by 16 f square xi1. Again, for a sample of size n, sample median is defined as mn as the rth order statistic, where r is taken as the greatest integer contained in n by 2 plus 1. So, if m denotes the population median, then it follows from the asymptotic distribution of sample order statistics that square root of n, that is large sample distribution of mn, is again normal with mean m and asymptotic variance tau square, where tau square is nothing but 1 by 4 times f square xi2, where xi2 is the population second quantile. However, we have already discussed asymptotic distribution of general order statistics. Now we shall discuss asymptotic distribution of extreme order statistics. In fact, we have assumed so far that square root of n multiplied by r by n minus p tends to 0 for p belonging to 0, 1, but for extreme order statistics, that is for r equal to 1, n minus 1 or n, r by n either tends to 0 or 1. Thus, we need to develop the corresponding asymptotic distribution separately. However, as earlier, we start with the joint asymptotic distribution of extreme order statistics for uniform samples. Specifically, if ui are IID rectangular 0, 1 variables, we require the joint asymptotic distribution of u ordered 1 and u ordered n. So, take an and bn as positive constants depending only on n, and consider the probability, joint probability, that an multiplied by u ordered 1 greater than x and bn multiplied by 1 minus u ordered n greater than y. Since the joint probability that an u ordered 1 greater than x and bn 1 minus u ordered n greater than y implies all observations are between x by an and 1 minus y by bn, we get the final expression as 1 minus y by bn minus x by an whole to the power n. Of course, if 0 less than x by an less than 1 minus y by bn less than 1 is satisfied. Thus, it seems sensible in this case to take an and bn as n, and hence as n tends to infinity, the above inequality is satisfied for positive x and y. Thus, for positive x and y, the limit of 1 minus y by n minus x by n whole to the power n is e to the power minus x minus y. Hence, we find that the joint asymptotic distribution of n u ordered 1 and n 1 minus u ordered n is the joint distribution of y1, y2, where yi are IID exponential variables with mean unity. Now, for a general development, first assume that k by n tends to 0, that is k is fixed. It is already proved in lemma 1 that for fixed k, u ordered k and tk by tn plus 1 has the same distribution, where tk is the partial sum I from 1 to k yi, and yi are IID exponential random variables with mean unity. Since yi are IID exponential random variables, we have by weak law of large number that tn plus 1 divided by n converges in probability to 1. Hence, by Slutsky theorem, n multiplied by u ordered k converges in distribution to tk. Since tk has a gamma distribution with rate k and shape with rate 1 and shape k, we have n times u ordered k converging to a gamma variable with rate 1 and shape k in distribution. Next, assume that k by n tends to 1, that is k equal to n or n minus 1 for example. For simplicity, we consider only k equal to n. Then from lemma 1, u ordered n has the same distribution as tn by tn plus 1. Then n times 1 minus u ordered n has the same distribution as n times 1 minus tn by tn plus 1, that is has the same distribution as yn plus 1 divided by tn plus 1 divided by n. Now, as earlier, from weak law of large number, it follows that tn plus 1 by n converges in probability to 1, and hence from Slutsky theorem we find that n times 1 minus u ordered n converges in distribution to a gamma variable with rate 1 and shape unity. In a similar way, for k equal to n minus 1, one can find the large sample distribution of n times 1 minus u ordered n minus 1 as gamma with rate 1 but shape 2. 2. So finally, we find the large sample distribution of sample range and mid-range for uniform pattern. Let ui be IID rectangular 0, 1 variables, and we want to obtain the asymptotic distribution of sample range u ordered n minus u ordered 1 and mid-range u ordered n plus u ordered 1 by 2. We have already derived that for uniform sample n times u ordered 1 and the joint distribution of n times u ordered 1 and n times 1 minus u ordered n converges in distribution to the joint distribution of y1 and y2 where yi are IID exponential with mean unity. Hence, using the delta theorem with gxy as x plus y, we observe that nu1 plus n into 1 minus u ordered n, that is which equals n times 1 minus Rn, has the same distribution as y1 plus y2 as n tends to infinity. Now y1 plus y2 has a gamma distribution with rate 1 and shape 2, and in a similar way one can find the distribution of the mid-range as the distribution of half times y1 minus y2, where y1 y2 are as earlier IID exponential with mean unity, and it can be shown that this y1 minus y2 by 2 has a double exponential distribution with location parameter 0 and scale parameter half. So in our last module we have discussed asymptotic joint distribution and asymptotic distributions of sample order statistics, and also obtained the large sample distributions of some sample summary measures based on order statistics. So in our next module we shall discuss something different what we have discussed so far. Actually, we have discussed the large sample distributions and for different types of sample summary measures, and in our next module we shall discuss their applications in actual inference. That is, what is the implication of the fact that some sample summary measure is asymptotically normal while the idea is to perform a testing of hypothesis. And then we shall pass on to another interesting context which is known as variance stabilization, and we shall discuss also the improved convergence rate through variance stabilization.